Okay, thank you. So basically today we are going to talk on the system modeling of A-PHY, a physical layer. And I'm Rajkumar Nagpal and I'm coming from Synopsys and I'm the co-chair of MIPI A-PHY. And so basically the title of the presentation is very clear. Actually, this is going to be a system modeling discussions and I'm going to say how do we really, as a proof of concept, use these models to write the spec. And these models are actually available to the contributing members, and there are some dedicated documents like an application note. You can have a look on these. And actually, this is more like a lot of things are very confidential, so I cannot put in the slides because this is a public domain, communication. So people who have some questions basically can put your questions. I will try to speak instead of writing here in the slides, which will be going in public domain. So I will try my best to reply your questions. So next slide, please. Okay, so basically A-PHY is actually coming in two, profiles. So profile 1 and profile 2. And basically profile 1 is basically NRZ, modulation. And profile 1 is basically for gear 1 and gear 2. So my colleague Ido just explained in previous session how the A-PHY profiles are divided. So basically, just as an overview, there are gears in A-PHY. So gear 1, 2, 3, 4, 5. So these gears are based on the data rates. So lower the gear, lower data rate. And for gear 1, 2, and optionally 3, there is basically a profile 1 implementation. And for gear option 3, 4, and 5, there is a profile 2 implementation. And the difference between these two profiles is basically profile 1 is basically targeted for low cost applications. It is targeted not to be so strong in terms of EMC domain. Okay, its EMC ability is a little less compared to profile 2. And performance wise, profile 2 is more, optimum for high performance applications. And of course, profile 2 come with a higher cost. Profile 1 is a low cost implementation and it has got some low performance compared to profile 2. Okay, so that's as a beginning. So there are two system models which I'm going to share. System model for the profile 1 is actually implemented in ADS, and ADS is basically a key site tool which we all use for architectural development. And basically the model of ADS for profile 1 basically includes your generator, encoder, and transmitter. Okay, so basically A-PHY is a full duplex physical layer. Okay, so that means apart from full duplex capability, it is capable of transferring the power. So there is a power delivery also allowed. So basically it's a bidirectional data communication with power delivery. Okay, so there and then so being a full duplex system, it is having a downlink configuration and an uplink configuration. Primarily downlink is for the high-speed data communication, and uplink uh, link is primarily for control, data communication. Okay, and power delivery can happen from either way, either uplink or downlink. Power, it depends, upon the implementation, whether it's a camera or display. Okay. So power delivery can be from either side. Uh, the channel is AC coupled. Okay, so channel is AC coupled, and rest is like when you are really doing the modeling of profile 1. There are other noise sources basically, which I'm going to share in the next slide, but these are the basic building blocks of a profile 1 system model. It is having a transmitter on my left side and a downlink transmitter and an uplink receiver. Okay, this is this configuration. Then your channel. Channel is basically your ENIS, basically end node interconnect structure. Then channel, then ENIS. This is actually a complete channel plus CPAPs. Okay, so this is complete channel. And then on the right side is basically your downlink receiver and uplink transmitter. Okay, so this is your uplink transmitter path, and then this is your downlink receiver. Okay, and then you have got basically, you can understand like there is always, these two links are always alive, so there will be coupling, crosstalk, echo, and there are mechanisms to cancel those, and those things are important to appreciate. Okay, so this is a very top level. So can we go to the next slide? Okay. So this is little deeper, like wherein we are putting the noise sources. So in the downlink domain, your orange is your downlink, and then you are actually adding a lot of noises here. Like in an automotive industry, the basic difference from a normal physical layer, which we are doing in general in our basic, physical layer, the differences here is that we have got automotive noises, which are EMC noises. So these noises we need to take into account in our model, like POC is a power over coaxial noise. So whenever you have a power delivery, happening from your maybe source to sink, this is going through a DC to DC converter, which is going to generate your ripple. And this ripple is, although being a capacitive coupled link, will be having some frequency, and so this will be actually going in both, transmitter and receiver. Okay, so this noise is going to be present. So this noise we are actually modeling and keeping as POC. Then the other noise is bulk current injection noise. It's basically when in an automotive environment, uh, primarily there are two kind of noises. One is static and another is dynamic. Okay, so when I say static noise, means the set of noise sources which are always present and which you cannot switch off. Okay, so it's more like always present kind of noise sources. Even when you are doing an initial training or equalization training or CDR training, these noise sources are present. Okay, so in those noise sources environment, your link should be capable to work, should be able to lock, and should be able to retain the required symbol error. Okay, so the static noise sources are like crosstalk. The crosstalk is coming from two sources. One level of crosstalk is coming from your um, interconnect channel, wherein like you have in an automotive environment, you have got a harness wherein your all the um, data networks are running, and you have got this coaxial line are running with multiple things binded together to really save your space. So there is a automotive harness is going to generate a crosstalk. Okay, and this crosstalk is generally we call it bundle crosstalk. This is going to be there. And then there is another degree of crosstalk coming from your ENIS structure, which is interconnected, which is basically AND node interconnect structure. This is actually a small PCB. This is also going to have in a multi-channel configuration going to add your crosstalk. Okay, so there are crosstalks, which is basically a part of your static noise. There is some A-PHY noise. Your receiver will always have some noise, so which we call analog front-end noise. Then you have got uplink, residual echo. So whenever you have got uplink, because uplink is going to be always active, so there will be some uplink noise, which you will be able to do some noise cancellation. Uplink noise canceller, your pattern, so you can basically subtract this noise to some extent, but it is going to be present. So this is unavoidable. So POC, crosstalk, A-PHY, uplink, car noise, these are all always present noises. These are static noises. Another category of noises are PCI, RFI, RF ingress, and large transient noises. These are not always present simultaneously, and it is expected in the simulations that only one of these noise sources is present at one moment of time. Okay, so you validate your system model taking each one of these one at a time, and you validate your static noises as always present. Okay, so this is the kind of integrated noise environment you have to consider in your system model. Okay, and then really the building blocks of the receiver are like, you have got a filter, like why do you need a filter? Because you know the spectrum of your uh, desirable signal and spectrum of undesirable signal, and you really tune your filter like it's a it's like a band pass filter. It has got HPF and LPF component, so you will tune it in a way that you are actually maximum rejecting the noise environment and accepting the signal spectrum. Right. So this is a band pass filter. Then you have got CTLE, and then you have got a DFE. By the way, this is profile one, and modulation is NRZ, and this is a very basic building block. So basically, this is a system model which is developed in A-PHY. Okay, and you can see here whatever I showed in my previous slide is actually implemented here in an ADS environment. You have got a transmitter, and then you have got a channel. Okay, and then you have got, these are the static noises which are always present, and this is a set of dynamic noises wherein you will switch it on one at a time, and this is your combiner. Okay, and this is like a gain block. This is your filter which I shared with you. Then you may have a CTLE, and this is your DFE implementation. And by the way, you will tune the DFE coefficients for your eye opening. Okay, and if you have your CTLE block, basically this is a gear 3 implementation where CTLE was not really helping, so we removed it. But for gear 1 and 2, you will have a CTLE block, and you will really tune your CTLE to really have your best eye opening at the slicer input. So this is all, is a very basic building block, and actually there are optimizers which we use. And this is a combined channel model wherein all the S parameter of ENIS channel, another ENIS and CPI are concatenated. And by the way, this is all available to the contributing members of MIPI. There is one dedicated application note really to explain all this implementation, and in fact this whole environment is available for anybody and who want to really validate or really appreciate more how the spec is developed. So this is all is available to MIPI members. Okay. So this is like a profile one, gear one, like an eye diagram before and after, after CTLE, after DFE, and then this is your um, analog front and band pass filter, which is generally tuned based on your I mean, so you can make it tunable or you can make it fixed. It's your implementation. And by the way, both are possible. So this is gear one implementation. This is gear two, wherein you have, by the way, whatever I'm showing here is the receiver front and transfer function, which is basically your AC response. And this is the eye diagram at the slicer after the CTLE. And this is gear two. Okay. Similarly, you can have a gear three also. So this is all I just discussed profile one. By the way, there's a major difference in profile one and profile two. Profile one, your EMC noises, whichever noises I shared, like static noises or dynamic noises, there is no, you have band pass filter and you have got CTLE and DFE to really handle and optimize your equalizers, and whatever rejection you need, you have a band pass filter. That's the way you handle it. But profile two, wherein the noise sources are much higher than profile one. Okay, and so here you need to have some sort of noise cancelers. Okay, so this is basically a profile two gear 5 system modeling system model, which is actually implemented in MATLAB. You can implement it in MATLAB plus Simulink. Okay, it depends. Your implementation can be either way. Okay. Probably implementing in EDS will be difficult because it is going to use some algorithms for, basically it is going to have your FFE and DFE and algorithms, which is LMS, sign, or whatever algorithm you use for your tap coefficient optimization. And basically, apart during the tap coefficient optimization, you really have an option. You really need to do a narrowband interference canceller. So it has to do the role of MBIC. So this is actually a DSP file. It is actually quite different from Profile 1.5. Profile 1.5 is a basically a more like generic file, which is all we use for normal implementation, a physical layer. Profile 2 physical layer is basically a DSP file wherein you have got you need to really optimize your receiver, and there are a lot of DSP algorithms. I can speak a little bit. I cannot put it here because of being, confidentiality. If you are a member, you already know. But since it's a public domain, so you can ask in separate. We can try to really speak here instead of writing. Okay. So basically, your transmitter has got a jitter, and basically this profile 2 is a PAMX modulation, and gear 5 is actually PAM16 modulation. So you have got a generator, which is PAM16 generator with some jitter. Okay. And then generally, like in an automotive file, your physical layer should not really emit a lot of PSD. So because of pulse spectral density requirements, you have got a max TX amplitude, which you can transmit. Okay. So this is here. I'm not writing those numbers because of confidential. So this comes to your, channel. Basically, you take an impulse response of your channel, and then you have got aggressors. This is your aggressor crosstalk. This is your POC ripple. This is your receiver noise, car noise, NBI generator. This is your uplink noise. Okay, A-PHY replica, echo cancel noise, large transient noise. Okay, all these noises are you see here, and they are going here into the receiver A-PHY model, and then you have got a DSP block. So by the way, whenever you are doing your optimization and whenever you are tuning your FFE and DFE coefficients, you really are in a training mode. Okay, generally this you do in PAM2 configuration, wherein you have got the maximum SNR, and during that stage you are really tuning your tap coefficient, and at this stage you are basically creating a notch for the NBIC, and this notch is basically going to kill your NBI. Okay, basically primarily handling NBI through FFE, DFE is important, and this is the most important aspect of this A-PHY system model. Okay, and then after that it goes to a slicer, and slicer decisions come back to the equalizer, and equalizer has got algorithms which are really optimizing the tap coefficients. So this is the basic, very top level profile 2 system model, and I think this is all. And this is the kind of scatter plot you get at the slicer, and these are actually the AC response of this is 1 by channel. This is your band pass filter. Okay, so this is without dynamic noise. Okay, and when you add the dynamic noises, your AC response appears like this. So this notches, it's actually having dual tone NBIC. To really handle dual tone NBIC, you are actually having dual tone and notch filter, which is basically going to be automatically tuned by your algorithm, which is LMS science and algorithms. Okay, so this is all at the very top level. I have tried to explain how this system model is working. And I think this is all for the today. And if you have any questions, you can ask me.
Okay, Raj, thank you for your presentation. So yes, you have questions, please submit them via the Q&A box as soon as possible, please. I guess the first question, Raj, does the system model include all of the noise sources included within the specification? And I guess the question is anything missing?
Yeah. I think this system model is really taking care of all the noise sources which are defined in the specification.
They're all there, great. Okay, and I think you mentioned that all this information is in what MIPI calls an application note that accompanies the A-PHY specification. Are any updates planned to the application note in the near future?
I think it may get updated with the A-PHY 1.1, but generally A-PHY 1.1 has not changed much from system modeling perspective, okay, because it is now dual link implementation. But system model wise, I think this is sufficient for both even 1.0 and 1.1.
Okay, it's good. That's good to know. Okay, one question is coming in on the Q&A. FFE and DFE taps are so large for MBIC. How can we implement it?
So generally, like here, generally this system model is having around 50 FFE and maybe 80 DFE types. Okay, so generally you need to have large number of taps because you really need to cancel low frequency noise also. So generally cancellation of noise, more the number of taps you have, better is the impulse response and better is the noise rejection. Okay. So more the taps, better is going to be your performance. So it is to really get a good performance and good rejection, you are using large number of taps.
Okay, thank you, Raj. Another question has come in. If model is not available for non-MIPI members, the suggestion is you can't then apply or won't be able to implement the SerDes chips. I think the answer there is obviously to implement a SerDes chip, you'll need to be a MIPI member, and therefore you will have access to the application notes. So I think that's quite an easy one to answer. Raj, do you have anything else to add there?
I think you have already replied, Jan, correctly. I think without being a MIPI member, if you are thinking of implementing A-PHY, I will say it is not going to happen clearly. Without a proper specification in hand, I don't think you can even try to do that. Don't try. You have to be MIPI member, and then you will appreciate a lot of technicalities, and then I think it will be more appropriate.
Absolutely. And on that subject, I mean, there are different membership levels. Our membership team would absolutely love to speak to you if you're not a MIPI member. Talk to us. There are different levels of membership, and they're designed to suit different needs, membership needs, depending on what you're trying to do. So please get in touch with us if you'd like to explore those options. Okay, another question. PAM2 is used during the entire startup. PAM16 is not used in startup. Are we expecting receiver to work in normal mode without equalizing the receiver on PAM16? I don't quite understand that, Raj. Do you understand that question?
I think maybe I think the audience want to ask is like, just I can reply again. So basically, whenever you start this physical layer, in the beginning, you do the training. Okay. When you do the training, you do it in the PAM2 mode. Okay. Because you get better, labels. Okay. Separation of the labels, you get better SNR. You have got better, like things are easier because things are in PAM2 mode and your rejection, your tuning, everything will be faster. You have got less ambiguity. Okay. That is the objective we do. And then exactly, you need to really do your LFSR, capture, like LFSR on TX and LFSR on RX need to be in sync. So all these things happen at the training stage. Then only you will know what is the pattern expected, what symbol is expected. And whenever you're doing the error calculation, you don't need to do blind adaptation. You know your expected symbol, and you can do true adaptation. So your true adaptation will be faster and more effective compared to blind adaptation. And that is why this whole scheme is developed so that you are able to do fast adoption. You come down to PAM2, then you go to PAM8 or 16, like that. So I think this is the easiest way.
Okay, Raj, thank you. So if anyone, another question's come in. I was just going to ask if there are any last questions. Why is TX equalization not mandated and more burden in RX? Equalizer?
Yeah, I mean to say this is maybe it is like this. Whenever you do the TX equalization, definitely you are enhancing the high frequency and you are attenuating the low frequency. Okay. So in a way, it is actually similar. Like you have an equalization at RX or TX, you really have not much of the difference. Only thing is, sometimes cameras are going to be like TX. Okay, you don't want them to be very complex. So generally, attempt is to keep RX complex than TX. And with that perspective, you don't want to make anything very special on the transmitter side. So it's more like a camera which will be basically generally a transmitter, and you don't want to make that device very complex. Receiver is going to be your application processor, ECU, which are like large socks. They are capable of really having everything. And generally, power is also less concerning in your socks than your peripheral sensors. So all these are the reasons we thought it is better not to really put any equalizer on the transmitter side.
Okay, Raj. Well, I think we've reached time. Thank you for your presentation and answering those questions. And obviously, thanks for your time today.